Here's a question that sounds like a trick, but isn't. What did humans actually eat before they had fire? The honest answer involves a surprising amount of raw meat, a genuinely impressive variety of insects, and a digestive system that was far tougher and far less picky than the one you're using right now. Before fire, eating wasn't the safe, predictable activity it is today. It was a constant negotiation with raw biology, bacterial risk, and the hard problem of pulling enough calories out of food that hadn't been transformed by heat. So let's walk through what was actually on the ancient menu, why it looked the way it did, and what it tells us about a stretch of human history that doesn't get nearly enough attention. First, the most important thing to understand. Fire is, in evolutionary terms, extremely recent. Modern humans have existed for roughly 300,000 years, and our broader genus, Homo, stretches back close to 3 million years. But the consistent, deliberate use of fire as a routine tool appears to have become widespread somewhere between 400,000 and 1 million years ago. That means for an enormous chunk of hominin history, millions of years, our ancestors ate an entirely raw diet. Not as a lifestyle choice, because it was the only option. Let's start with meat, because it's one of the most consequential parts of the story, and it happened long before fire. Cut marks on animal bones made by stone tools used to butcher carcasses show up in the archaeological record at least 2.5 million years ago. Some evidence pushes even earlier. That means hominins were eating raw meat for well over 1 million years before they had any way to cook it. What did that actually involve? A lot more chewing. Raw muscle fiber, connective tissue, and cartilage are mechanically tough, significantly harder to break down than cooked meat, where heat has already begun softening the structure. This is part of why early hominin skulls show such large jaw muscles and oversized molars. The physical demands of eating raw, tough food required genuinely powerful chewing equipment. That anatomy softened over time as cooking reduced the need for it. Then there's the bacterial and parasitic risk. Salmonella, E. coli, Listeria, various parasites. Modern food safety guidelines exist precisely because raw meat is genuinely dangerous. Early hominins were exposed to all of this with none of our modern safeguards. How did they survive? Their gut physiology was likely more aggressive at killing pathogens than ours is today, shaped by millions of years of exposure. And honestly, the second answer is less comfortable. They probably didn't always survive. Illness and death from contaminated food were almost certainly a real and regular part of life in an environment already defined by high mortality from every direction. Beyond muscle meat, organ meats would have been especially prized. Liver, kidney, brain. These are much softer and easier to eat raw, while packing extremely high concentrations of nutrients. Bone marrow deserves special mention. The archaeological evidence for deliberate bone breaking to access marrow is extensive. Those percussion marks on ancient bones aren't accidental. Hominins were cracking bones open on purpose. Marrow is essentially pure fat, calorically dense, and would have been one of the most efficient raw energy sources available. There's also the question of how meat was actually acquired. A significant body of evidence suggests early hominins relied heavily on scavenging, accessing carcasses already killed by other predators. Scavenged meat ranges from relatively fresh to well into decomposition. Many scavenging animals, like hyenas and vultures, consume heavily decomposed meat without apparent harm, and early hominins likely did the same out of necessity. Plant foods made up the bulk of calories for most hominin populations across most of this period. But eating plants raw comes with its own serious challenge: starch digestibility. The most calorie-dense plant foods available, tubers, roots, underground storage organs, contain starch in a crystalline structure that human digestive enzymes struggle to access efficiently when raw. Cooking disrupts that structure through gelatinization, breaking starch granules open and dramatically increasing what the body can absorb. Studies show a meaningful percentage of raw starch simply passes through undigested. So how did pre-fire hominins get enough calories from plants? A few ways. Mechanical processing, pounding, mashing, thorough chewing, helps a little. Fermentation, even if unintentional, improves digestibility. But probably most importantly, early hominins likely leaned more heavily on foods that didn't have this problem. Ripe fruit contains sugars the body can absorb directly. Nuts and seeds are mostly fat and protein. These foods don't face the same digestibility. The picture that emerges is a pre-fire diet that probably emphasized fruit, nuts, seeds, and leafy material more heavily than the post-fire diet did, with tubers and roots becoming dramatically more nutritionally useful only after cooking became routine and made their energy actually accessible. Insects deserve more attention than they usually get in these discussions. They were accessible, reliable, and nutritionally dense and required no cooking whatsoever. Chimpanzees, our closest living relatives, use tools to extract termites and ants from nests, and the behavior is well documented across multiple study sites. Termites, ants, grubs, beetle larvae, these would have provided year-round fat and protein with relatively modest effort for the caloric return. Honey is worth a specific mention as one of the most calorie-dense foods that exists, requiring zero processing to be fully digestible. The challenge wasn't the food itself, it was getting past the bees defending it. But when accessible, it would have been an extraordinary raw calorie source. The human body itself has preserved a physical record of this dietary transition. Relative to body size, the human gastrointestinal tract, particularly the colon, is notably smaller than that of our closest primate relatives. This is widely interpreted as a direct consequence of cooking. Once cooking began reliably pre-processing food, a smaller gut became metabolically viable because less digestive infrastructure was needed to extract the same nutrition. This connects to one of the more compelling arguments about human brain evolution, the expensive tissue hypothesis, developed by researchers Leslie Aiello and Peter Wheeler. The argument is that the human brain's unusually large size was made metabolically possible specifically because the gut shrank to compensate, freeing up the metabolic budget a larger, ape-like digestive system would otherwise have consumed. If that's right, a hominin population still dependent on a raw diet and a larger gut was operating under tighter metabolic constraints on brain growth than later hominins who had access to cooking. Dental evidence supports all of this. Microwear analysis, studying microscopic scratches and pits on tooth enamel applied to early hominin fossils, consistently shows wear patterns consistent with tough, fibrous, raw food. And not all early hominins ate the same way. Some species, particularly within the genus Paranthropus, showed jaw and tooth morphology, suggesting extreme specialization toward hard, fibrous plant material. Others in the early Homo lineage show less extreme dental specialization, consistent with a more varied and flexible dietary strategy. That flexibility, rather than anatomical brute force, appears to be the path that eventually led to us. One dimension of this story that rarely gets discussed is water. Fire didn't just transform food. Boiling water kills the vast majority of waterborne pathogens. Before fire, hominins drinking from rivers, streams, and ponds had no equivalent protection. Waterborne illness, stacked on top of foodborne illness risk, created a genuinely demanding disease environment that early hominin populations had to survive in for millions of years, relying only on physiological resilience and accumulated knowledge about which water sources tended to cause problems. Food storage is another underappreciated piece. Without smoking or drying, both of which require fire, raw meat begins decomposing quickly, especially in warm climates. This almost certainly shaped social behavior. If a large kill or scavenged carcass can't be preserved, the optimal strategy is rapid, wide distribution, share it now, consume it fast, build reciprocal, social obligations with the people you share with. That kind of meat-sharing behavior, extensively documented in modern hunter-gatherer societies, may have roots that predate fire entirely, driven originally by the simple fact that unpreserved meat rots. Nuts and seeds, by contrast, store naturally due to low moisture content and protective shells, giving them strategic value beyond their nutrition, functioning as a buffer food that could be gathered during abundance and eaten gradually. Tubers occupy an interesting middle ground. Many can remain viable in the ground for extended periods, effectively providing a natural food bank that required no preservation technology at all. What modern individuals who follow strict raw food diets show us is instructive here. They tend to have lower body mass, and particularly in women, increased rates of reproductive disruption, generally attributed to insufficient caloric intake. Raw food, even chosen deliberately, with full knowledge of nutrition, is simply harder to extract calories from. It was not some secretly superior ancestral strategy. It was a genuinely more difficult, more risky, more costly way to survive. And hominins did it for millions of years because they had no alternative. What they did have was behavioral flexibility. Early hominins were not especially fast, strong, or well defended against predators. What they had was the capacity to strategically assess their environment, use tools to overcome processing challenges, shift dietary strategy as conditions changed, and tolerate risks that less cognitively sophisticated species might not have navigated. The millions of years spent eating without fire were not simply a deprived prelude to the real story of human development. They were the proving ground where the behavioral flexibility, strategic thinking, and accumulated practical knowledge that defines our species were actively being built. One raw meal, one foraged tuber, one scavenged carcass, and one handful of insects at a time.